So thanks everyone for attending this P4 GSoC wrap-up meeting. So today we are excited to have our 4 contributors giving their final project presentations. So I just wanted to say a few words before that part to summarize this year's GSoC program. So this is our second year participating in Google Summer of Code, or GSoC in short. So we are very happy to see that we have successfully completed 4 projects in the end. So I want to give a big thank you to all the participants in this year's People GSoC program. This includes our 4 contributors, Shivi, Vinet, Advay, and Sanko. Thanks for your contributions in general, and congratulations on completing your project. I think that's a great achievement. And also, if you would like to stay with the community and keep contribution, that's awesome. But if you have other plans and would like to move on, that's also understandable. And we wish you best luck in whatever you plan to do next. And we wish you have learned something useful from the GSoC program. And you are always welcome back. Also, I would like to say thank you to all our mentors this year, especially the primary mentors who have probably spent a lot of their time, like on the projects, to make sure they're on track and to resolve any issues. And this includes Matthew, Mingyu, Anas, and Murayim. So thank you for volunteering your time, and also thanks to all the mentors. And lastly, I would like to thank all the organ means and also several other community members who helped organizing the program in general, like setting up this meeting. And yeah, overall, thanks all of you for making this happen. So looking forward, we are likely to continue doing the P4GSoC program next year as well. So we would appreciate if you can help us attract more contributors. So if you see anyone who might be a good fit as a contributor, just encourage them to apply next year. Also, we would appreciate anyone who would volunteer to be a mentor next year. So either if you are a mentor this year and you found it to be a great experience and you want to do it again, that's great. Or if you are a contributor this year, but you probably learned a lot of things here and you might have some great project ideas. And we also encourage you maybe to be a mentor next year. And also to anyone who just sees this and would like to participate as a mentor for the first time, you're all encouraged. So lastly, let us know if you have any suggestions that could help us improve. So that's all I wanted to say. Now let's move on to give the spotlight to our contributors and to give their presentations. So our first presenter is Xiyu. So Xi, please take it away.
Sure. Thanks, Billy. Okay. Good morning, everyone. My name is Xu Hao. I'm currently a master's student majoring in computer science at New York University. And my research interest is around distributed systems and BFT problem in particular. I also have a strong passion in networks and compilers that lead to my interest in P4. And here is a quick recap on our project and project goals. So we are trying to build a final mechanism or mode for action selectors. And for instance, action selectors could be used to implement features like ECMP. And here is a simple example that we use a trivial round-robin mode for ECMP. Like there exists 3 egress ports, and traditionally, when a packet comes into the ECMP construct, it will obtain a single resulting output packet by selecting one of the egress ports. But our goal is to obtain all 3 possible header states and have them flow downwards to the pipeline as if they are normal packets, as the figure shown on the right-hand side. And why it matters. So we envision 2 use cases for it. The first one is diff testing. So we can compare the results of deployed P4 switch with the simulated results we gain from BMV2. is quite helpful for fast program and selector behavior validations, and this is especially for hash functions. And also, since the mode is try to generate all possible header states, it's a deterministic behavior, so we can build better test coverage out of it. Cool. And here is fanout in action. And when someone wants to use the mode, they should just add it to the hash algorithm enum defined in v1model.p4. So it is not a standard mode supported by v1 model, but a customized mode supported by BMV2 core in particular. It's similar to how round robin was implemented before. So it was also only supported by BMV2 core and not added to the standard v1 model. So anyone wants to use it, just add the mode to the v1 model and use BMV2 to process it. And here is a quick run through of our general architecture. So let's take a look at the right-hand side. And this is an overview of the, say, ingress thread. And when there is the input packet gets pushed to the ingress, then the ingress thread will pull the packet from the ingress buffer, and the packet will get processed by the parsers, and the program will define a set of tables, like the whatever the initial table is, and the packet will go through the pipeline until it hits a action selector. Action selector will match the packet headers against the table as well, and then choose a member from the matched group. When this behavior happens, we change to the left-hand side. So the action selector will actually query our customized fanout selector asking, which member should I apply to this input packet? The fanout selector will actually implicitly invoke the fanout packet manager, who captures the context when such matching happens, and also try to replicate n-1 fanout packets, where n is the number of members in that matched entry. And then the original packet will get processed by one of the member and continued in the pipeline. After the original packet gets processed, our fanout manager will push the replicated n-1 packet back to the ingress buffer. What is different this time is that when the ingress thread pull a packet from the buffer, it will not go through the parser and initial node. It will just start from the continuation node, where we define continuation node as the whatever table that will be applied to that packet after the action selector it was derived from. Cool. Here is a quick demonstration. So in this instance, we have a multicast table in the ingress thread, and we have a table with action selectors in the egress thread. And when a packet goes through the multicast table, the multicast group will be set to the packet, which will replicate for, in our case, 3 egress packets to three different egress ports. And within each egress thread, the packet will be replicated for fanout for 3 actions, resulting in 3 different packet states. So here we can see that on the rightmost part, we have a green box and 2 light-colored boxes, where we have the concrete line representing the so-called original packet we just shown on previous slide, with the dashed boxes representing the fanout packets get replicated for the action selector. And to make the observability better, we also built new tracing events. So every time there is a packet gets replicated for fanout, the event called fanout gem will be triggered, and we can obtain such information, like the parent packet copy ID, which is you can understand it as the parent packet ID, and also its own packet ID after replication. So we can build out of a derivation tree out of the tracing we built. Of course, one thing to add is that here are 6 final gen events triggered. The reason is that if we recall the overview architecture, we have n-1 packets gets fan out, gets replicated for fan out. In this case, it will be 3-1, which is 2. And since there are 3 egress packets gets pushed to the egress thread, it's 2 times 3 equals 6. So there are 6 fan out gen packets. However, there will be 9 output packets in total because we have 3 egress ports times 3 actions gets enumerated or fan out at the end. So there will be 9 packets in total. Cool. That's basically a quick overview and a quick wrap up of our project. Please let me know if you have any questions.
I was wondering, what if your original program keeps any state? Do they packet copies? I guess citizen, yeah.
So it's actually a great question, and we indeed encountered it during implementation. So I think there are 2 aspects to the question. So the program could be stateful, like it might use, say, meters or counters, which are essentially stateful. And the package may also maintain some metadata, which are kind of stateful, right? We did not solve the issue for the former one. And for the packet states, we simply replicate everything the packet has. Like metadata is also encoded as PHVs in BMV2. So we essentially copy that state from the packet. But yeah, it's hard to maintain the state for stateful constructing the program. We leave that unsolved right now.
That's okay. Thank you for asking. Thank you for clarifying this.
Yeah, thank you.
Yeah, thank you, Xi. Let's welcome our next presenter, Vinit.
So, hello everyone. Myself Vineet Goel, and my project is related to P4 simulator, enhancing the control plane. So, before starting, let me give you a brief introduction of about me. So, I am an undergrad student at Indian Institute of Technology, Roorkee. This is my first time contributing, and I just love to play video games. So, before starting, let me give you a background about what is the project. So first of all, what is NS3? NS3 is a discrete event network simulator, which is used for research and education in computer networking. Basically, you can create different simulations in networking with the help of NS3 framework. And what is P4Sim? P4Sim is a module in NS3 that helps you to work with P4 programmable switches. So before this project, in P4Sim, there was only the data plane and there was no feature of control plane. So my goal for this project is to build a control plane feature in the P4Sim module. So these were the results for my GSoC project. The key contributions were mainly a P4 controller class, which manages and multiple switches and flow tables during the runtime, the data collection and tracing mechanism, some tests and example use cases for the project, and lastly, the documentation. So this is the architecture of P4 simulator. The black box, which you can see, which is in bold, is the P4 SwitchNet device, which represents a switch in real life. And in that, P4 switch core is kind of like an architecture which is installed on the P4 switches. Right now, the P4 SIM module has three architectures, the V1 model, PSA, and PNA. And in the blue box, you can see the P4 controller, which is the feature which I have to implement in this project. So first is the control plane features, which I have to implement. So what I have done is I have used the BMV2 APIs, BMV2 switch APIs, which are there in the P4 repo, and I have added the wrapper functions in the P4 controller class. So what I have done is I have added the wrapper functions for P4, basically the BMV2 switch APIs in the P4 core. And to use those functions, I have added functions in P4 controller. So P4 controller is like your controller in real life, and P4 core is the switch architecture. And here is a screenshot of some of the header file codes, which you can see where I've implemented the wrapper functions. So moving on to the next feature is the event handling via trace mechanism. So the main and key feature of this project was to enable a runtime communication between switch and the control plane inside the NS3 simulation. So this feature was, I basically used trace source mechanism, which is a feature in NS3, which helps you to add event listeners and events in your basically network modules. So what are trace sources? Trace sources allow the switch to emit events during the runtime, and the controller or any other object can use those trace sources to connect to the switch and can listen for the events. And once the event happens, the controller or whichever the device you have connected with the switch can call a callback function, which you want to implement when an event happens. So moving on to the third feature, which was writing tests and examples. So I have written the tests for flow entry tables and TTL management. And I have also added example use cases for trace source mechanism. And basically the picture on the right side shows one of the example use cases. And for basically it shows how you can write tests in P4Sim. So this basically the block code of this code shows the how you can test the action profile functions, which is implemented in the P4 simulator. So in last, let me just give you a whole how this control plane and P4 simulator works. So initially, using a function which is the register switch function, you can register your switches in the control plane. The control plane will connect to one or more P4 switches, and during the simulation, you can listen for the events. And once the event happens, the controller's callback handler will take those events and basically perform the certain functions. The type of events which can happen are like throw entry is installed, a packet is processed, or a DDoS attack is happened. Whichever you may like, you can add that event and listen for those events. Also, you can see on the right, uh, and basically here are the logs when an example use case is run. Here you can see initially the simulation run and it logs the how many switches and at which port they have been added. And then I have written certain functions which help me to add table entries in different switches. And here are the logs once the functions are successfully executed. So the main impact of this project is that a control plane is supported in P4Sim now, and it can help researchers prototype an SDN-like control, write and test more about P4 programs, and brings P4Sim closer to a real-world simulator for P4 switches. So some of the future work which can be done in this project is currently I have implemented basically the control plane for V1 model, but the P4Sim still lacks the control plane implementation for PSA and PNA architecture. The tests, I have added the APIs, wrapper APIs for each and every BMV2's API, BMV2 functions, but still I have written the tests only for the flow entry operations. So the tests for other functions are still pending. And obviously you can write more and diverse tests to test all the functioning of the P4 switches in P4 simulator. And in the last, I would like to acknowledge my mentors and organization for the guidance. And I'm planning and excited to keep contributing after the GSoC also. So I'm open to questions now.
Okay, if no questions, our next presenter is Advay. Yeah, so please start, Advay.
Yeah. Okay, just to make sure. You guys can see my screen, right?
Yes, no problem.
Okay, so hello everyone. I'm Advay Singh. I'm an undergraduate at the University of Michigan. This is my first time contributing to an open source project of this scale. Yeah, I'm sort of broadly interested in systems, architectures, networks, and compilers. Thus, I wanted to contribute to the P4Ling consortium. So let's talk about data centers. In a lot of data centers, the final hop isn't these actual end nodes or servers, but servers are actually in virtual machines. And then once you have network packets which have to be routed to these virtual machines, there's a lot of packet switching, which is traditionally done in a virtual switch. So this virtual switch, such as OVS, which is one of the most common virtual switches, routes these final packets to these different virtual machines for each node. However, this takes a lot of CPU cycles, very CPU intensive, because for every single network packet, you have to do a lookup on which virtual machine this belongs to. Recognizing this problem, people developed hardware offload using serial input-output virtualization. This essentially allows you to offload some of these packet switching rules off directly to the hardware. However, the hardware does have a lot less space, so a lot of cache misses tend to occur where you have to use a virtual switch. And again, you run into the problem of high CPU cycles and a lot more time again. So this is where GigaFlow comes in. GigaFlow leverages the pipeline locality of these OpenFlow software pipelines and also rules-based reusability for these hardware caches to achieve much higher cache hit rates. So sort of the architecture for GigaFlow looks like this. The key idea here is to break the OpenFlow pipeline into multiple different subtraversals, which the flows can share as they're going through the hardware. So on the right, you can see how the initial OpenFlow pipeline is broken into these subtraversals. Using these subtraversals, you have these longest traversal matching rules, which multiple flows can, with different traversals, can actually share in these GigaFlow caches, which are on the SmartNIC. So these GigaFlow caches look sort of like this. This is the P4 code. So each GigaFlow cache is just a P4 table with certain rules that they match on. So here you can see how there's one exact match field, which is a table tag. The table tag corresponds to the current table in the virtual pipeline. This is required to ensure correctness, and this is also why it's called the longest traversal matching rule, because you want to match on the longest subtraversal in the software pipeline. The rest of the fields are standard OpenFlow ternary fields, and we have pretty standard actions so far. However, you can extend these actions in future versions. And then the whole cache tends to just be a pipeline of these GigaFlow tables. So as you can see on the right, you have the application of all of these GigaFlow tables. And in the end, we just basically, anytime you have a hit or a drop, we tend to set this table tag to a sentinel value like a 254 or 255, basically indicating that it's a hit and we don't want to send this packet to the CPU or the virtual switch for an op call. So that's what you can see on the bottom right there. So what was the problem before the summer was that GigaFlow is only a software emulation. So there was proof of concept. You can see that this has higher cache hit rates and this sort of architecture would work, but we actually just had to offload it to hardware. So with the help of my mentors, I implemented this offload in the AMD Alveo U250 FPGA board. And by doing so, I also created a template for hardware offload for GigaFlow caches on P4 enabled devices. So the timeline and deliverables for the summer look somewhat like this. Initially, I wrote the GigaFlow tables in P4, as you saw previously. And then using the AMD P4 to SDNet compiler toolchain, this was compiled into this SDNet IP, which was then used as a broader net FPGA shell to generate this full RTL design. Using AMD Vivado Design Suite, I generated a bit stream, which I offloaded onto the AMD Alveo U250. So now that we have the actual bit stream, I created a AMD SDNet driver. This driver basically just kind of installs rules for this bit stream. with the fields that are supposed to match. However, there was still like a need to transfer or translate the rules from this open flow pipeline down to something that the FPGA and the SDNet driver would understand. That's why OVS actually had to be modified as well. So once OVS was modified, we could finally install P4 rules into these Gigaflow tables. So the infrastructure, as I was creating this, looked somewhat like this. So there was 3 nodes. There was a collector, a Gigaflow enabled OVS, and a TGen. The collector just installed traffic and OpenFlow rules into the OVS and TGen, and it collected logs at the end just for metrics. The actual network interface card for the Gigaflow enabled OVS was the AMD Avio U250. And then it would install cache rules onto that, and cache misses would be reported back up. The net FPGA received and transferred traffic to Mellnox NIC, which was the network interface card for the TGen. And the results look somewhat like this. So as you can see here, the number of upcalls with Gigaflow offload decreased significantly for most of the pipelines, as opposed to the traditional OVS, which only has the Megaflow caches. However, keep in mind that we can also leverage the previous software Gigaflow emulation alongside this hardware offload to have even less upcalls. So the value in this, well, Open vSwitch is the most popular virtual switch in the world. Its improvements have been incremental. So originally realizing that the user space took way too much time rather than just the kernel data path, microflow kernel caches were introduced, but they had zero reusability. So megaflow kernel caches, which allowed for some ternary fields, were introduced. And then just to have this user space actually just be able to communicate with the network devices directly, DPDK was introduced with the OVS architecture. However, this didn't allow people to reuse some kernel infrastructure, so AFXDP, and then, as I previously mentioned, serial input-output virtualization. But now it's time for Gigaflow. So for the future work, as I mentioned, I created a template using this AMD card. So now it's time to actually be able to offload into other fields and other network interface cards and DPUs as well. Some of them being AMD Pensado and NVIDIA Bluefield. Basically, any P4 enabled device can support this. Yeah, and I'd like to take a moment to thank all my mentors and all of everyone here involved for being a part of the consortium and helping me throughout the process. And thank you, and open to questions.
I have a question as to, do you see there is a difference between like the hardware target you have experimented with, which is FPGA based, I believe, versus the two DPUs you mentioned at the very end, which I believe are not FPGA based? Do you see there are significant differences in those?
So actually next I wanted to work on the Bluefield DPU, the NVIDIA Bluefield DPU.
Yeah.
The actual offload I think is a lot easier because they just have like such a nice API, Docker API and all of that, rather than having to go through, create this whole bit stream and all of that. So I think just the idea is that I'm not sure which, like how the performance is going to be yet. I'm excited to see what that's going to look like compared to the FPGA, but just programming ease wise, I think they are easier to implement.
I see. Yeah. Yeah. Thanks for the explanation. Salvato has a question. Do you want to just ask in the video?
Yes, I can. Thank you. Thank you very much for the presentation. Could you please quickly remind us, I think this is a Gigaflow detail, how you translate pipeline into Gigaflow tables?
Yeah, so this was the main part of like the Gigaflow algorithm originally, and this was already there in the software emulation, where it's basically you would have this OpenFlow pipeline, and then every time that a packet misses and is an upcall, as it goes through the pipeline, you basically break down the pipeline, seeing what resources you have available, like which Gigaflow tables you still have available. You break down the pipeline into these these different subtraversals with their different rules. And then those rules have to be lowered even further to just be like the matching fields that are offloaded to the net FPGA.
Okay, so there is an automatic mechanism. You don't do it manually.
Yeah.
Okay, cool. Thank you.
Mm-hmm.
Okay, thanks, Alve. I think I don't see any more questions. So let's welcome our last presenter, Sanko. Please go ahead.
Here we go. So myself, Sankalp, and this time my project is Split Decision Tree, Scaling Stateful Decision Tree Algorithms in P4. And a little bit about me. I am pursuing IT from Bachelor's of Technology, Ajay Kumar Garg College, India. And I'm highly active in local communities at Delhi, such as I co-organize myself in colleges as Google Developers Community. Also, I lead a little bit in table tennis. While I also, as I mentioned about community efforts, I do anchoring and content writing for those community events. And this is my debuting time in open source with P4. Well, about the project overview. So Split is a research project. It's a Switch native compiler framework that enables stateful decision tree inference directly in programmable switches, bringing real-time machine learning into network data planes, which means like it compiles high-performance decision tree models to enable detection and observability of security significant flow behaviors across diverse traffic overloads. So while working on this research project, there was a conventional problem that ASICs have very limited stateful memories. So when we're having conventional decision trees, what they tend to do is they tend to fill up entire stateful memories. And as that happens, that often makes a bottleneck such that only the limited top k amount of features are only used for actual inference. Now doing inference for particular topics like malicious and benign packets, now that's not really a great part. And there what our uniqueness come in split decision trees. So what we propose in this research project is a partition decision trees. It's the same decision tree, it's the same binary decision tree, but what we are doing is we have divided it into a small subtrees. And hence like each subtree is having their own IDs, and that's where the term SID comes in, like subtree IDs. So as you can see, each triangle shows the different subtrees acting over that same conventional decision tree which you saw earlier in the previous slide. Now what happens is in this kind of decision trees, the incoming packet flows are divided into two windows. So the partition lines above part have the first window and the later part gets the second window, which we'll discuss later. And the project architecture of our research project looks like it has majorly three pipelines called as split compiler, split generator, and the control plane, and plus the data plane part. So as an overview, it goes as like split compiler. It gets input as the data set, and we understand like what kind of target we use. Here we are using Tofino. The split compiler has CIC flow meter for data extraction, feature extraction, hypermapper for optimizing to provide the best partition decision tree models, which in return provides some dot files or like how that partition decision tree models work as that gets fed up into a split generator. The split generator using all those dot files create a P4 program files, which in return goes to the P4 compiler, gets compiled, provide .pinfo files and the target binary. At the same time, there is a control plane working around. Now, before coming to control plane, we also you have to create the pickle files, which we are going to feed in the control plane. For the pickle file part, we actually got the inspiration from the old research project, the previous working research project, which was inspiration for this particular one called as NetBeacon. We use their particular part that how they convert the dot files into the pickle versions of it. And the control plane using P4 runtime or B4 runtime, depending upon our target, depending on the data plane drivers, and using gRP communication, we are able to install all the TCAM rules and SID rules into the data plane. And we can see in the control plane that we can see the outputs in the form of digest, like whether the incoming network was malicious or benign. So the implemented core framework looks like that. So there's a difference between this slide and the previous slide, is that this slide was particular about the entire project, and this is more about the how much is implemented as of now. Now, as you can see, there are totally three colored bifurcations. One is about model compilation, the pink one is around code generation, and third one is runtime deployment. And if you have seen this, there's an anomaly in this figure, is that the first model compilation is not actually directly attached or like connected to this to the rest of the pipeline, and it's a very important reason for that. It's basically, as of now, we are not yet we are not actually using the first model compilation pipeline into the entire system. And as of now, we are only using the custom decision tree models. These are handmade written models, and but the output of these are also in the same are very similar to the what the first model will provide. The first model is basically, as I mentioned before, it's a CIC flow meter, hypermapper for optimization. It does training, and it also have a Grafana Postgres monitoring analysis to understand like how the data sets were perceived and what kind of percentage they are and all the statistics about the data. And they also provide the same, but they provide the optimized partition DT models. They got the .json files and pickle files. And as of now, we are using only custom DD models with their respective .json files and pickle files. Coming to the second pipeline, the code generation and standardization. So in our code repository, there is a folder called as utility, in that we have three subfolders as filter, netbeacon, and p4 code gen. Filter is more about feature mapping, as the incoming packet features versus how they will be mapped to the stateful features. And in this case, in this project, we are providing three stateful features, which is summation, minimum, and maximum. So that mapping happens in the filter part. The netbeacon part, as I mentioned before, it's basically a TCAM conversion based on the research project which we found through the previous research, and the P4 code gen. So this P4 code gen is a very straightforward Jinja2 based Python library. It's able to provide a P4 program, which in case gets fed up to the third pipeline, the final pipeline. So this pipeline is having a control plane and a data plane. This data plane, depending upon what kind of driver we opt for, either we are using for the TNA version or the BMV2 version, we are able to compile that part, and the compilation will provide the .pm4 file plus a target file. And if it's a barefoot version, the OpenSSD version, then it will provide a pipe which will have the all the configuration files with it. The control part. Now here, our barefoot runtime controller is dynamic. So depending upon how many stateful features we are going to use, that many automatically gets dynamically allocated. And using the gRPC, they're getting installed in the data plane. And also, if we send the packets via interface, then we can see a deployed model providing inference at digest. So there's a small sample partition decision tree. If for being specific, it's actually E1 example, which I'm referring over here with the repository. So this is a simple partition decision tree, and as you can see, there are 5 SIDs: SID 0, 1, 2, 3, 4. And so here we have assigned that the F1 will be stateful for summation, F2 will be stateful for minimum, and F3 feature will be stateful for maximum. And in this, if we give the inflow of the first window of packets with the 4 features as F1, F2, and F3, and all these 5 features values provided, as you can see over here. So the first part goes into the SID 0, as the control plane starts from the SID 0, the parent node, the root node. And here that is stated as F1 is less than equals to 3000. Now the stateful F1 means the entire F1 summation, and that which is like 150 plus 300 plus 250 plus 400 plus 600, which is of course less than equals to 3000. Thus the control forwards to the truer part of the child node, which is the F1 less than equals to 2000. Now here again we are checking whether the F1 is less than equals to 2000. Now we are checking again with the same thing, the stateful part, And again, the 150 plus 300, 250, 400, 600 sum is not equals to 2000. Thus, we go to the this particular part and the SID2. And now, since it's on the partition line, we go to the second window packets. And in this window packets, we can see here like we have now what happens in the stateful memory, that existing first window features, incoming packet features are all getting deleted, and the new packet features are getting installed in that memory. Thus, we are reusing the same part again and again rather than clogging up entire memory. And here again, so assign inside E2 for F1, 100 plus 50 plus 30 plus 100 plus 90. That sum will not be like less than equals to 2699. Thus, we will move to the false side, F3. And here we are checking F3 is less than equals to 100. Since I am told that F3 is the stateful for maximum, and the maximum is 50, 90, 10, 60, 90. So the maximum is 90 over here, and 90 is not less than equals to 100. So that makes it to the truer part, and thus it becomes benign. Thus the inference will be flagged the flow as benign part. So this is a small representation of how our entire split will be working, and that's pretty much it. The future scope is that it has just to be deployed on the Ansible playbooks for automating all the environments. Moongen implementation for more diverse traffics, for stress testing and the real environments, and the decision tree pipeline integration, as I mentioned before in the architecture, that the first pipeline is not yet still integrated with the second and third one. So that part is yet to be as a part of a future scope. And yeah, that's pretty much about it. I'm open to all the Q&A session, and really I'm grateful for all the opportunity provided by the P4 from the GSoC side, from the entire community, and especially shout out to my mentors, especially Maria ma'am, for helping me out for may I have for like such as like since P4 is having a very high skill gap. So like mentors really play a very key role over here, because LLM can't help. Documentation only helps a very limited if you are very new to the new stuff. So yeah, open for questions. Yeah.
Okay, any questions from the audience? Yeah, thank you, Sanko.
All right, thank you, sir.
Let's see. Yeah, if there are no questions, I guess we can conclude today's meeting here. So thanks everyone for participating and presenting your work.